Okay, so in this video I'm going to be talking about solving sets of nonlinear equations. In previous video I talked about solving sets of linear equations, so maybe we had n linear equations with n unknowns. And to solve that, we put these equations into matrix form. So we had a coefficient matrix multiplied by an unknowns vector called the solution vector was equal to some constant vector. And this we called an AX equals B problem, and we employed just matrix methods. So solved with matrix methods. Like Gaussian elimination or LU decomposition, things like that. So, but in this case, I have two equations here. This is my first equation, my second equation. And I have two unknowns. So two equations with two unknowns. My unknowns are x and y, okay, but they're nonlinear, meaning that the unknowns are raised to some non-zero power, like x squared showing up here and here, or I have cross terms where I have x multiplied by y. And so I can't formulate this into a set of matrix equations like this linear set of equations over here. So how do I solve a set of nonlinear equations and find out the solution? What x values and y values might satisfy this equation? Well, you might remember from our discussion before that in a previous video talking about linear systems, that we talked about systems of three variables, so three unknowns and three equations, and how each of those equations represented a plane, and we might have three planes, and they might intersect all along some point. Doing a bad job of drawing planes here. I'm supposed to have three different planes here. So three planes. They all intersect at a single point. Well, now, if we had three nonlinear equations with three unknowns, these planes could be very curved. And we might get them, one plane that looks something like this, has some kind of curvature to it, and another plane that intersects with it somewhere. And so we might have many solutions that exist. We might have no solutions that exist, or we might just have a single solution that exists. But with nonlinear equations, the probability of having many solutions exist goes up. Just because we're much more likely to intersect in several places than in just a single place. Now, that's obviously not always true. There's some family of nonlinear equations such that when you combine them, maybe this statement isn't true. I'm not going to try and go be very mathematically rigorous and prove this statement or something like that. I just want to give you a feel for the idea that what solutions might represent in a kind of a graphical sense. So if I wanted to solve this set of equations here, there's two sets of nonlinear equations, I have a couple of different approaches that I could take. Okay, methods. Let's talk about methods for solving sets of nonlinear equations. Okay, so one approach that you could take is you could try and find a transformation that makes the system linear. Some equations that works. For example, if I had the system of equations that was x equals y squared and y equals minus 5x xy, well, I could take the natural log of both sides, and then I would get the ln of x equals 2 times the ln of y, and then over here I'd have the ln of y would equal the natural log of minus 5xy. Well, that's just equal to the natural log of minus 5 plus the natural log of x plus the natural log of y, using logarithm rules. And now I could define two new variables. I could call x prime is equal to the natural log of x, and y prime is equal to the natural log of y. And then this system of equations up here just becomes, if I substitute in here, this is x prime right here, x prime, this is y prime, so I would get y prime equals 2 times, this is x prime. So x prime equals 2 times y prime, and then y prime equals x prime plus y prime plus the natural log of minus 5. So now these equations are linear. So I have two linear equations. But coming up with a transformation that puts your equations in a linear form, it's rare that you're able to do that. And it's not always obvious how you would do that as well. So another approach, so this approach, is hard.
And that's just the first sentence of the paper. Two separate groups have done 3 experimental settings.
This approach is hard and not always possible. Not always possible. Okay, so if that's the case, what are we going to do? So let's write down our equations here again. So x equals y plus x squared minus 0.5. That was our first equation that I had written up there. And then y equals x squared minus 5xy. So the other approach is, what if we just approximated these equations as linear? So can we approximate the equations as linear? So if we can approximate them as linear, then we could solve that approximation for the answer, and after we solve that approximation for the answer, we could then take that approximation and plug it in and get a better approximation. Does this kind of sound like root finding methods? Well, it should, because that's essentially what we do with root finding methods. So maybe if we had this equation up, this first equation up here, just one equation, well, no, that doesn't work. So if I had one equation and one unknown, say f of x was equal to the natural log of x minus x squared, that was equal to 0. So that could be written like this: ln of x equals x squared. This is a nonlinear equation with one unknown. So one unknown, one equation, we should be able to solve it. We did. The way we solved it was we turned it into a root finding problem, and then we used something like the Newton's method. So this is our function f of x that we're looking for a root. The solution to this will be the solution to our nonlinear equation. Maybe it comes down like this. Well, maybe we give it an initial guess called x0. Okay, and we can draw a tangent line here, and that represents us linearizing the equation. Linear approximation. And then finding the solution to that approximation here, x root, was our approximation to the solution of our actual linear equation. Well, when we have two unknowns and two linear equations, we can do the same thing. Now, you guys might remember that one approach here, this is kind of describing the Newton-Raphson method. Newton-Raphson method. Well, we derived the Newton-Raphson method derived using Taylor series. So what we did was we said, okay, we've got our function f of x, let's approximate it as a line. We can do that by writing out the Taylor series. So let's do this for f of xi plus 1. So our next guess was equal to f of xi plus xi plus 1 minus xi times f prime at xi. Right? Then we said, okay, well, where this line crosses the x-axis, that means this is 0. We'll let that be our xi plus 1. So here I'm letting this be xi and this being xi plus 1. We said let this be 0, and then we can solve for xi plus 1. Okay? In terms of f of xi and f prime at xi. So at our current guess. So in high dimensions, we're going to do the same thing. We're going to linearize, come up with a linear approximation. So approximate high dimensional function. High dimensional function as linear using the Taylor series. Alright, so in order for you guys to kind of follow this next part, I need to introduce you to some new notation. So writing down our equations again, we had x equals y plus x squared minus 0.5, and then y equals x squared minus 5xy. Well, I can think of these two nonlinear functions as one vector valued function. So I'm going to write this vector x, and the vector x is just going to be an x and a y point. Okay? So in 2 dimensions you could think of that as x here is a vector. So say I specify this is x and this is y, then some point here is going to be represented by this vector that points out to this point, and it's going to have a x component and a y component, right? So I could rewrite this these equations as a vector valued function. So this is my function, and it returns a vector, and it takes a vector as input. Okay, so x is just going to be this x right here is this x up here, so it's 2 components, and then it's going to return a vector of, we could call this vector this function f1, and this one f2. But before we do that, we would need to move everything to one side. So first, we move all terms to one side. So we might move this term over to this side of the equal sign, and this term, the y, over to this side of the equal sign. So our f1 of x would equal y plus x squared minus x minus 0.5, and then f2 of x would equal x squared minus 5xy minus y. Okay, so this vector value function, it takes an x and a y value, and it returns, for its first component, it returns f1 of x. Okay, plug in your x, y values to this first equation right here, and you're going to get back some number, and that number is going to go right here as the first component of the return vector. And then the second component is going to be f2 of x. Okay? So now what I need to do is I need to take a Taylor series expansion. So let's take a first order Taylor approximation for our big vector value function f. Okay, f that takes a vector x. Now that sounds probably kind of crazy to some of you, but it's pretty simple. All we have to do is write down the Taylor series expansion for each one of these equations. Okay, so Taylor series for this one, and then the Taylor series for this one as well. And those it'll be a vector that has the Taylor series for the first function as the first component, and the Taylor series for the second equation as the second component. So let's do that. So let's find the Taylor series expansion of f1. So f1, remember, it takes a vector x. So I'm going to expand it about a vector x I. It's my centering vector, and we're going to predict it at a point xi plus 1. So xi plus 1. Okay? So f1 at xi plus 1 is approximately equal to the f1 at xi this is a vector now, plus the derivative of, now we're talking about partial derivatives now, the partial derivative of f1 with respect to the very first variable, so with respect to x, evaluated at xi. Okay, so we're evaluating this derivative at xi. Then we're multiplying it by the distance between xi plus 1 and xi, just the components. So we have xi plus 1. This is not the vector, so this is the component. The component of xi. Okay? So, xi plus 1. Okay? Minus xi. And then we're going to have plus, we need to do the partial derivative with respect to f2 with respect to y. This is also going to be evaluated at xi, the vector xi, times y I plus 1 minus yi. Alright, so that is the Taylor series expansion for the first equation. Now we'd have to do the Taylor series expansion for the second equation. If we do that, we get f2 evaluated at xi plus 1 is approximately equal to f1 at xi, the vector, plus partial of f2 with respect to x evaluated at xi, so vector xi, times xi plus 1 minus xi plus the partial of f2 with respect to y evaluated at xi times yi plus 1 minus yi. Alright, now we know that we're going to approximate this where these two functions are going to be equal to 0. So where f1 evaluated at xi plus 1 is equal to 0. Okay? So we're essentially setting both of these sides equal to 0. That's what we did when we derived Newton-Raphson method for the one-dimensional case. So if we set both of these sides equal to 0, what we can do is we can rearrange these equations, and I'm going to kind of take some liberties here and not go through all the algebra, but basically what I'm going to do is I'm going to take these components right here and move them over to the other side. So this component here, and move it over to the other side, and then this partial derivative of f2 at xi, this is just a scalar. So these derivatives right here, this derivative here, and this derivative here, and this derivative here, and this derivative here, once they're evaluated, they're being evaluated at some point x, so I'm going to pass in an x and a y value here. That's what that xi means. So these derivatives are just going to become a number, a scalar. So the partial of fi with respect to xi are scalars. That's important to know. Okay, so in the next step. So now I'm going to have f1 at xi negative is equal to, let's just write this out. We had, for the first equation, we have f1, alright, yeah, we'll write it out. So we're going to have the partial of f1 with respect to x evaluated at x equals xi, kind of changing notation on you here, times xi plus 1 minus xi plus the partial of f1 with respect to y evaluated at x equals xi times yi plus 1 minus yi, right? Now, oh man, see the negative sign there? Okay. Then the next equation we get minus f2 evaluated at xi is equal to the partial of f2 with respect to x. This is evaluated at the vector x equals xi, and it was multiplied by xi plus 1 minus xi plus the partial of f2 with respect to y evaluated at x equals xi times yi plus 1 minus yi. Okay, now think of this as this right here. This is just a delta x, and this is just a delta y. Okay, and so those are our unknowns. That's what we're solving for, right? We really want to figure out what our xi plus 1s and our yi plus 1s are in terms of the other things. So what we can actually do is now I have kind of two unknowns. So two unknowns and two equations. So our unknowns are the xi plus 1 and the yi plus 1, and everything else is known. This derivative evaluated at xi is known, and our yi is just going to be some, yi and xi are just going to be some initial guess. Okay? So I can rewrite this in matrix form. When I do that, I get the following equations. So I get some vector that has this f1 evaluated at xi, the negatives, and then f2 evaluated at xi. So this vector, this matrix, is going to be equal to this matrix here, where I've got the partial of f1 with respect to x evaluated at x equals xi, and then I have the partial of f1 with respect to y also evaluated at x equals xi. And then over here, down here, partial of f2 with respect to x evaluated at x equals xi, and partial of f2 with respect to y evaluated at x equals xi. So that's our matrix here. Whoops, didn't mean to chop that off. Multiplied by our unknowns vector. I'm going to call this the delta x vector. Delta x, where I've got delta x and delta y right here. Where the delta x vector, so this delta x vector, delta x, delta y, this is equal to xi plus 1 minus xi, and yi plus 1 minus yi. Okay? So what we do is, this is just a linear set of equations. This is like a constant vector. So this is a b vector equals some matrix that is just full of numbers, coefficient matrix. So A times a unknowns vector. So we get AX equal to B, which we can just solve using Gaussian elimination. And once we solve and we get the delta x vector, we know what the xi vector is. That's just our current guess. We can solve for xi plus 1 using this equation. So now we know we solve for delta x, so we know this. We know this. And we also know the yi values and the xi values. That's our initial guess. Well, we can just solve for these xi plus 1 values. So we can say xi plus 1, yi plus 1, put that in a vector. That's equal to our initial guess, which was just xi, yi, plus this delta x vector that we solved for. Delta x, delta y. Alright, now we've come up with an approximation. To do it, we had to use this set of matrix equations right here to come up with our delta x vector. And this matrix right here is a very special matrix. It's called the Jacobian. Jacobian matrix. Okay, it's full of each equation gets its own row, and each variable gets its own column. So you need to calculate the Jacobian, and then once you calculate it, you have to evaluate it at your current guess, and then solve the system of equations for the unknowns, and then that'll give you your approximation. So let's actually do that for this original problem. So the original problem was, our two equations were, well, let's write them out. Let's see here. So we had f1 of x comma y was equal to y plus x squared minus x minus 0.5. So remember, I moved the x over to the right hand side, so all of this is equal to 0. And then f2 of xy was equal to x squared minus y minus 5xy. That was equal to 0 as well. Alright, so let's calculate the Jacobian. So when we calculate the Jacobian, so calculate Jacobian, we get the following. So the partial derivative of f1 with respect to x, that is equal to 2x minus 1. And the partial of f1 with respect to y, that's just equal to 1. Now the partial derivative with respect of f2 with respect to x, that's going to give us 2x minus 5y. And then the partial of f2 with respect to y, that is going to give us minus 1 minus 5x. Okay, so now I can actually put these into the Jacobian. So the Jacobian matrix actually looks like this. So J equals f1, the partial of f1 with respect to x, remember, partial of f1 with respect to x. So I'm going to just put that in here. So that was equal to 2x minus 1. And the partial of f1 with respect to y was just equal to 1. Now the partial of f2 with respect to x was equal to 2x minus 5y. And then with respect to y, it was minus 1 minus 5x. Alright, now this Jacobian right here is a function of x and y, which is what we expected, because we should be able to pass in an x value and a y value, and then this will just be full of numbers. So the Jacobian, for example, evaluated at x equals 1 comma 1, so 1, this is my x value, my y value, that's going to be equal to 2 times 1 minus 1, 1, 2 times 1 minus 5 times 1, minus 1 minus 5 times 1, which that matrix then becomes 1, 1, 2 minus 5 is minus 3, minus 6. Alright, there we go. So I have this equation here. I know this, multiplying this by a delta x vector and a delta y vector should give me the a vector full of the negatives. So remember, negative f1 at x, y, and negative f2 at x, y. So that's equal to, if I plug in 1 into my first equation, here's my first equation. If I plug in 1 into this equation, so I get f1 of 1, 1, 1, right? That's equal to 1 plus 1 squared. So 1 plus 1 squared minus 1 minus 0.5. That's going to be equal to, well, these cancel, that's just equal to 0.5. And then f2 at 1, 1. What's that equal to? Well, that's equal to 1 squared minus 1 minus 5 times 1 times 1. So we get these two cancel and we get minus 5. So that's equal to minus 5. So coming down here, plugging these in, we get minus 0.5, and then minus 5 becomes 5, like this. And now we have a linear system. So this is our B vector. This is our coefficient matrix A. And this is our delta x vector multiplied by delta x vector. There's our linear system, which we can solve and get delta x. Then we can take that guess and plug it in to our Jacobian and get another guess and solve the whole linear system over again and repeat that process over and over until our delta x vector gets small, and that'll be our solution. Alright, so that kind of wraps up that idea. That was a long video. Hopefully it makes sense, and we'll see you in the next one.